grade 12s, you're here with me, Megan, on today's show on physical sciences, the Doppler effect. Now, I remember 5 months ago, I was sitting exactly where you are, very, very confused. And I know some of it's actually really confusing, but I'm sure Phil, I'm here with Phil, is going to explain it so well. So I'm excited, and I'm going to be here with you. I just want to give a shout out to Macmillan, our sponsors, for sponsoring this show. And if you have any questions, please feel free to contact us on facebook.com/learnextra. So let's get ready. Phil?
Thank you so much, Megan. Okay, well, guys, as you said, we're going to be talking about the Doppler effect today. So we're going to be doing a little bit of revision about waves, about wavelength, about frequency. Some of you matrics have either been on holiday or about to go on holiday, and you've forgotten all about wave, sound, and light. So I'm going to dump you back in the deep end. Some of you haven't seen this section before. Take some notes, get on the website, get our notes, and actually start following through on the show. The examples on the notes are exactly the same ones which I'm going to be talking you through tonight. In fact, I'm going to be taking you through some past paper questions which are relevant to this section. So let's jump straight into it. The Doppler effect. Well, before we get too far into it, what we're going to start doing is we're going to lay out the lay of the land tonight, and we're going to start seeing what we're going to be learning about tonight. So our plan of action tonight is to learn about what the Doppler effect is, how to apply the equation, and then to tackle an exam-style question right at the end here. So let's just start taking a look at some of these things which you can expect to see tonight. Well, first of all, the Doppler effect seems quite complicated, but it's quite easy if you start taking into account a couple of the steps that we're going to be showing you. Okay, now it's all about moving objects and the waves which they give off. So here we go. We're going to learn that objects that move relative to one another, that means that they're moving close to each other or further away from each other, causes a change in the observed frequency. Now there we go. We're talking about a change in the observed frequency. Now that sounds very fancy and sciencey, but basically it just means that if objects are getting closer to each other or further away from each other, and one of them is making a wave, the frequency is going to change on its way to the thing which is listening to those waves. Now, most of tonight is going to be talking about sound waves, but you can apply this to any sort of waves. You can talk about water waves, you can talk about light waves, you can even apply this to explaining the Big Bang to somebody, which is really cool. Okay, then what we're going to do is we're now going to apply the Doppler equation. And now this is where you guys are going to get most of your marks. And the Doppler equation, which is something that looks really fancy again, but if we start to deconstruct it and look at it slowly and do it carefully, and that's what we're going to do today, it's going to become a lot easier and a lot less intimidating. So here we go. We're going to apply the Doppler equation to solve examination questions, and then we're going to jump into past paper examination questions. Hopefully, we're going to get some time. I'm going to answer some of your questions as well related to the Doppler effect, but it's really not that hard when you follow some easy steps, and we're going to show those steps to you later on. Okay, so now let's go into a little bit of background theory. Let's start talking about what actually means to have a source of a wave, what a disturbance is, and we're going to start to see what its effect is on the frequency which actually happens to come off this object. Okay, so most of you recognize the very sort of simple question and the simple sort of example that I've given you on the screen here. We've got a source of waves. Now, cars are very noisy objects. They like to give off waves. Now, one of the things that can happen is, and I'm hoping this happens to most of these cars, is that cars can move. So cars can move along, and since there are sources of waves, we're going to start to see that that actually affects the way that we hear the waves which come off the cars. Now, most of you have experienced Doppler effect before. You've heard a siren of something going past, or you've even heard a racing car which is going past. Now, most of you intuitively inside your head actually have recorded the Doppler effect inside your heads. Now, I want you to start thinking about either a race car going past, or you can start thinking about a siren on an ambulance or a police car which has gone past. You'll actually notice that the note or the pitch changes as it goes past. Our job now is to explain why. Now, here it is. Let's start paying attention to some of these things. And later on in the show, if you watch carefully, we're actually going to show you some really cool animations dependent on wavelength and frequency and how those are perceived. So let's talk about the object's wavelength and its frequency. Now, the wavelength of what? You might start to think about, what are we actually talking about? We're talking about the wavelength and frequency of the sound waves which are coming off this vehicle. Now, here's the problem. This source would be a very, very nice thing to study in terms of wavelength and frequency if the source remains stationary. If the car was just idling there, making a noise on one spot. But here's the problem. Sources like to move. And this is going to create a bit of a change in the way that these waves are going to come off. So what I'm going to do is I'm now going to move my source very slowly, and I'm going to move it stepwise. And then what we're going to do is we're going to study what happens to the waves which come off it. So what I'm going to do now is I'm going to start drawing some waves as they come off. So we've got this wave which is coming off the front of the vehicle. So it's going out in all directions. So what we're going to do is now we're going to study what happens when this wave moves out in all directions. Just to remember that waves move from the disturbance out in all directions. Now, it's going to create several of these waves as it goes out. And what you're going to find, and I've actually found a much better drawing than I could ever do, we've got this wave which is now coming out from the car. But now the car is going to move before it makes the next wave. So what you're actually going to find out is that the spacing between the waves is going to change. And here we go. There's a really nice drawing of it. And this drawing is inside the notes as well. So if you're not that great at drawing, what you'll actually notice is that as the car drives, something is happening to the spacing between the waves. So here we go. I'm just going to highlight what it is, and I hope that people at home are shouting out the answers. What is the spacing between the waves? And if you're watching the grade 10 show, which was great revision on our light and our waves and wavelength and frequency, we've been talking about waves to light and sound the whole evening. So Matrix, this is all great revision for you guys. The spacing between waves is called the wavelength. So there we go. The wavelength is a spacing between two consecutive waves. Now you can see there's a very, very wide spacing behind the car. So what I'm going to find is that behind the car, that these waves are actually much more spread out than in front. We can see the same number of waves occupying a much smaller space. So what we're finding is that they are further apart here. So we've got a much larger wavelength. But what happens in front of the car? What we can see is that these waves are much closer. So what I've actually done is I've now shortened the wavelength in front of the car, and I've stretched it out behind the car. And that's the result of the car moving. Now that's what I mean about relative velocities, and it sounded very technical. But basically, when something which is making waves moves, it's going to change the waves in front and behind it. And that's very important. This is going to lead to the Doppler effect. This itself is not the entire Doppler effect. All that we've done is we've shown what happens to the waves in front of a moving source and behind a moving source. So we've got the source which is now making these really weird types of waves, and they're squishing them up in front and they're stretching them out behind. Now you've got to think of yourself, how am I going to actually hear this? I don't get out a ruler when I measure these waves. I don't actually get, oh, okay, well, I see the car coming past. Let me get my ruler quickly. Let's measure the wavelength. What you experience and what your ears are good at picking up is the frequency or the pitch of these waves. And you might say, well, how do I relate wavelength and frequency? Now you're going to have to do a little bit of grade 10 revision and see that they are actually related to each other. In fact, I find both of them inside this equation. V is equal to frequency multiplied by lambda, and that's the wavelength. They are related to each other. Now what we've got to do is we've now got to say, well, if I change wavelength, how does it change the frequency? Well, the really nice thing for us is that we can assume that the velocity is going to be the same for frequency and wavelength. Now that might seem a little bit weird unless you start taking into account that sound has got a fixed velocity at a certain altitude. And for most of you, that velocity will be 340 meters per second. Now, that velocity can change depending on where you are. If the sound waves are going through slightly thicker material, that will increase. That means down at the coast, sound travels faster. And what you're going to find is that as you travel up and up and up, sound is going to travel slower because the particles are more spaced out. Now, not to worry too much if you weren't thinking about the physics microscopically of sound moving, not to worry. All I'm saying is that this velocity of sound in air is around about 340. Some of your textbooks might say 343 or might say 330. It depends on the situation, but they've got to tell you this. Back to our relationship between wavelength and frequency. How do I relate wavelength and frequency? Well, if I apply a little bit of simple grade 9 maths, I can rearrange my formula. If I say that frequency is on its own now, I can start to move things across. I can say that velocity is equal to, velocity over wavelength is equal to frequency. Now I can look at a relationship between frequency and wavelength. So what does it mean for our car over here? We've got a changing wavelength behind the car, and we've got a changing wavelength in front of the car. How does a changing wavelength change our frequency? Well, let's look at my formula here. Look at where our wavelength actually is. When the wavelength is underneath, it's underneath the fraction, it's a denominator. What's going to be the change if I make a denominator bigger? What will happen to my fraction? Well, my fraction over here is going to get smaller as the denominator gets bigger. So, what does this mean for our larger wavelength? The frequency will decrease. Let's apply our thinking to the shorter wavelength. What happens to the shorter wavelength? A shorter wavelength means a lower lambda value and a higher frequency. Now let's summarize all of that. So let's take a look at the actual Doppler effect and how it applies here. Now, there's many different definitions that you can apply to your Doppler effect, but basically it's to do with the change in observed frequency. So that means the change in the frequency which we can hear or observe or see. So it's the change in the observed frequency. So I'm looking for a change in the observed frequency as a result of the change in the relative velocities of source and listener. Now we're going to start taking a look at those two words. I gave you a source, but I didn't introduce the idea of a listener. So now let's take a look at those two situations. You can be in multiple positions. So what I'm going to do is I'm going to take a look at objects which are getting closer, and I'm going to be taking a look at objects which are getting further. So now let's highlight that on our screen. So now there's two situations. So what I'm going to do is I'm now going to put you in two different positions. So you can be listener A, which I'm going to now move. So let's move around our listener A, and I'm going to put listener A behind the vehicle, and I've got listener B over here. And take a look, our source is now moving towards listener B, and what I'm actually going to do is I'm going to see what the effect is on the frequency. So if you were in position B over here, so we've got position B, this is you, busy listening, waiting for the car to approach you. What you should notice is that we've got a shortening of the wavelengths here, a squishing up. So the car is actually squashing its own waves, making them shorter, making the distance between them shorter. So what does that do? That means that the listener, and that's you, is going to hear a higher frequency than the frequency which is given away by the source, which is the car. Let's just go through that again. The waves which are squished up, which are squashed closer together, the shorter wavelengths mean an increase in frequency. So in getting from the source to the listener, and that's the way the waves go, they go from the place where they're created to the place where they're observed or listened to, I find that the wavelength has increased the change in frequency. Now, how did it do that? The waves got smaller, or closer together rather, and that changed the observed frequency. So the listener is going to hear a higher pitch than the source actually gave out. Now let's see if this thinking helps us for position A, which is now behind the car. So let's just highlight that, and let's just make sure that that is on our screen. There we go. So now what we're going to find for objects which are getting further apart. So I am now listener A. Listener A is standing here behind the car with a smiley face. The car is now passed, and what we're finding is that the wavelength itself has now stretched out. That means that the wavelength is increasing as a result of the car leaving its own waves behind. So my wavelength gets longer. What is the result? Well, the frequency which you would hear at position A now means that the frequency is going to decrease. Wavelength gets longer, means that the frequency is going to get smaller. So wavelength up, frequency down. So what I'm going to find is that my wavelength is larger, and what that means is that the frequency gets much smaller. And that's great. If you can make this prediction, if you can apply your knowledge of the basic Doppler effect, that means that you're setting yourself up for success when you start to deal with the Doppler equation. The Doppler equation, unfortunately, seems to be the source of a lot of worries. So once again, when things are getting closer, the frequency increases. When they're getting further apart, the frequency will decrease. I think it's time for an ad break. What do you think?
I think so, but I've learned a lot already in this, 10 minutes maybe? It's crazy. So, mindsetters, I see that you're posting your questions. I'll talk to Phil now, and everyone says hello, by the way. So, I'll get back to you. Have an ad break, go drink water, come back, and be ready to tackle the Doppler effect, because we'll be with you all the way. See you after the ad break. Welcome back, grade 12s. You're here with me, Megan, and Phil, and we're going through the Doppler effect, and I'm actually physically understanding what is going on. So I hope you came back refreshed from your little bit of a break, and let's get going. Phil has a little simulation, and I love simulations, so I'm really excited, and I hope you are too. So let's watch.
Okay, well, thank you so much. Well, what we're going to do is now we're going to take a look at a short animation. Now, this animation is designed to show us the Doppler effect when something is moving along and making waves as it goes. Now, it's a fairly short simulation, but basically the whole idea is that I can now understand why the waves are actually crunching up in front of the object and stretching out behind. I think that was one of the questions posted onto our Facebook page. So now, as something moves, it's making those pulses, it's making those disturbances. Now, as it's moving along, it's following the ones in front, shortening the distance, but it's running away from its own waves behind it. Now, before I talk your ears off, what I'm going to do is I'm going to let the simulation speak for itself, and it's really, really cool, nice bright colors, and we can actually start to see what the waves look like when we've got a moving source. So now, this is a very short video clip, and in fact, you can just do a Doppler search on YouTube, and it'll come up. And it's really, really particularly nice. You can actually start to see, as the waves go out, I'm just going to pause it for a second. You can see that the waves in front are squashed up. They are squashed up, meaning that my wavelengths have shortened in front of the source. So this little dot traveling across your screen, making new waves. So I'm going to let it carry on for a little bit longer, just fill up your entire TV screen with some waves. And what we're going to do is we're going to see that the waves on the right-hand side of your screen in front of the source have now squished up. The wavelengths have shortened. While behind them, they've stretched out. That means that I've changed the wavelength. Now, if you're listening carefully before the before the break, I'm getting really obsessed here. Okay? So if you were listening before the break, you'll notice that wavelength and frequency are actually related. Now, how would the frequency sound if I was standing on this side, so in front of this object? Well, this object which is making the sound would now sound a higher frequency, or at least it would sound like it. But if I was standing behind it, in other words, it was running away from me, what I would hear is a lower frequency. So let's just go back to our summary. So we've got our lovely summary over here, which says that objects which are getting further have got a lower frequency. Now let's just make the same summary over here. So the frequency increases when objects are getting closer. And this is really important. This is the first step to solving any Doppler question, is when they get closer, the frequency will increase. So anytime two objects, so we've got a car driving towards observer at position B over here. So here's my happy observer, my position over here. That means that I've got a car traveling towards them. That means that the frequency is going to increase because the wavelengths are shorter. I hope that everyone understands that. Just to round it off again, what we're going to do is we're going to take a look at the situation. So when you're at observer A position, so there's our happy observer over there, what would you hear? Well, because the wavelength is getting larger, the frequency is going to get smaller. So that means a lower pitch, a lower frequency. Now, if you were starting to think about this before the break, you can actually sort of think inside your head. Now, unfortunately, I can't play sound through this board, but you can actually think about what happens when a racing car goes by, or if you start to hear an ambulance going past. Now, if you listen to that racing car, as it comes towards you, you've got that really high frequency because the two objects are getting closer. And when it goes past, it goes to a lower frequency. Now, the next time you see a racing car which goes past, you can actually make the sound with it. So it goes, and then as it goes past, it goes, So what you're actually noticing is that there's a change in the frequency. So as it approaches you, it's got that very high frequency, and as it goes away, it's got a much lower frequency. Now here comes the mathy part. And this is the part which they're going to ask you. But don't forget about this, because we're going to use our prediction, is the frequency going to get bigger or smaller, to actually answer the Doppler equation. So let's start getting into it. Now, the Doppler equation itself looks very intimidating. Basically, all it's trying to do is it's trying to calculate what is the frequency which the listener hears. Now, let me explain the parts of the Doppler equation. So now, first of all, why do I use the Doppler equation? Here we go. I'm trying to change the frequency from the source. So that's the frequency of the source. So let's just write it in as we go in. So that's the frequency of the source. Now, what I'm going to do is I'm going to isolate parts of this equation. So I've got the frequency of the source, and the frequency of that source, don't forget it's in hertz, is going to change when it goes to being the frequency which the listener hears. So there's the frequency that the listener receives. So what I'm going to find is that I can actually extend this to the pictures inside my question, and the frequency of the source is the frequency of the car, the original car. So the car which made this noise is the frequency of the source. Now, because the source is moving, I'm going to get a change from one frequency to the next. Now, this is where this big fraction comes in. Now, this fraction looks really, really complicated, but it doesn't need to be. I've got pluses and minuses and v's all over the place, but don't panic. So what we're going to do is we're going to write this out, and we're going to try and see what these pieces of this equation are. So what do these various velocities actually mean? Well, the velocities on the left are the most simple ones. That's just the velocity of the wave itself. If it's sound through air, it's 340 meters per second, but don't panic, you don't need to learn that, they need to give it to you. This is just the velocity of the wave. So it's the velocity of whatever wave you've got. Now, one of the people watching our show asked us, how do I apply this to light from stars? Well, if you were talking about light from stars, I wouldn't use the velocity of sound, but I would be using the velocity of light. Now, just remember, when you walk outside and you look at the nighttime stars, just remember that you're actually receiving light waves from space, from those original stars, billions and billions and billions of kilometers away. Now, somebody said, how do I actually apply this? Well, this very clever equation can actually show us how fast stars are moving relative to us. So are the stars in the sky coming towards me or going further away from me? Now, this equation can actually calculate how fast those stars are moving, and are they moving towards me or away from me? So that's what's so amazing about this equation. It can do a whole bunch of stuff. It can do astrophysics and can do everything, but most importantly, it can help you pass your matric exam. So now let's get you to that position. Now, what are these other two velocities? Well, I'm sure that most of you have actually managed to figure out that I can apply this to the velocity of my listener. Now, I'm very aware that some of your textbooks may not even show this top part of the equation, VL. Okay, now most times, that's saying I've got a velocity of my listener. Now, my listener, just remember our little smiley happy face guy? That's where his velocity comes in. So the velocity of my listener is a very important thing to consider, because I said the relative velocity between these things makes the Doppler effect. Now, where does Vs come from? Well, Vs is fairly easy to understand when you realize it comes from your source. My source is moving, so it has a velocity. Now you might say, okay, well, Phil, you still haven't explained the most complicated and really weird part of this equation, and that is the plus and the minus. So now this plus and the minus, how do I sort out? Do I use plus? Do I use minus? Do I apply like vectors inside here? I've seen 15 different methods from my teacher in the textbook. I'm going to show you the method that works for me, and it's probably the simplest method. What it applies is what happens to the frequency from source through to the listener. It needs to apply your knowledge. Does the frequency increase or does it decrease? Now, that's the first part of my stepwise program for sorting out a Doppler equation. So let's write down our steps as we go. The first thing I need to do is I need to predict, is frequency of the listener going to be bigger or smaller than the source? To do that, you need to really understand the Doppler effect. So I need to predict whether or not the frequency will increase or decrease. So is it going to be the frequency of the listener? Is it going to be bigger than the frequency of the source? Now, for those of you at home saying, well, when would that happen? Well, this is when objects are getting closer. So for objects getting closer, the frequency of the listener will be larger. They will hear a higher frequency. Or will the frequency of the listener be less than the frequency of the source? And that's when objects are getting further apart. Now you might say, well, why do I need to predict? Why do I need to describe what is going on? Well, this is actually going to help me with the plus and the minus. So what I'm going to do now is I'm going to say, well, I'm going to use my prediction to change my equation to be simpler. So now what I've got to do is I've got to change that fraction. I actually call that the Doppler fraction. What do I mean by the Doppler fraction? It's the thing which actually changes the frequency. So let's write out our Doppler fraction. So velocity of our wave plus or minus. Now I'm going to show you how to choose the plus and minus. Velocity of my listener, v plus or minus the velocity of my source. Now what I'm going to do is I'm going to change to line up with my prediction. So I need to change the fraction in accordance with my prediction. So we need to change the fraction so that it makes sense in terms of my prediction. Now that might not seem like something that makes a lot of sense, but what we're actually going to do is we're going to change the fraction to match my prediction. So whatever I do to this fraction, if I choose plus or minus, it must do what I predicted. So let me give you a bit of an example. If I say that frequency listener has got to be larger than source, this fraction has got to get bigger. Whatever I do to VL and VS must make my fraction larger, because I've made the prediction that that frequency listen must increase from frequency source. So this might not make a lot of sense until we start actually putting in some numbers. So we need to change the fraction to match my prediction. So what I'm going to do is I'm going to work you through a prediction and how to change this fraction. So let's say, for instance, I've got a particular instance where I've got a vehicle once again. So we've got our vehicle. Now you might see why I'm a science teacher, not an art teacher. So we've got a vehicle which is now approaching, and we've got a very unhealthy looking stick man, and the vehicle is approaching my stick man. Now remember that the vehicle is going to give out frequency source. He's going to hear frequency listened. So FL is what he's going to be receiving. Now here's the question. Will the frequency source and the frequency listened, which one will be larger? Well, because they're approaching each other, step one, this tells me that step one is, well, I've got objects which are getting closer, so that means that frequency listened is greater than, so increases from frequency source. That's very important. I know that the frequency will increase, that is going to be listened. Now something else important. Let's just make our velocity of our listener, let's make him 0. Let's not move him. So this is how most of your questions will be, that your listener will not be moving. However, I've got a velocity of my source, and that's very important, and that's why the Doppler is actually happening. We've got a moving object giving off waves, and that's going to change the frequency. So what do I need to do to my equation? Well, since I know that the fraction itself, the Doppler fraction, must get larger, well, let's alter it to help me out here. So V and V, these cannot change. This is the velocity of my wave. I haven't told you what it is, but we can assume it to be exactly the same as what they would tell us, and they will tell us in the question. And that's coming up after the next ad break. So get your pen and paper ready, because after that ad break, we're going to jump straight into the questions. But now let's explain this further. What is VL? Well, VL itself, so now what we're going to do is we're going to choose plus or minus VL, and we're going to choose plus or minus for VS. What we're going to do now is we're going to simplify that very greatly, and we're going to choose pluses and minuses, and we're going to put in some values. So now our velocity of our listener, lucky for us, was 0. So it doesn't matter if you choose plus or minus. But now at the bottom, this is where most of the action is going to happen. I need to choose a plus or a minus for Vs, which will make my fraction bigger. Let me repeat that. Whatever I choose for plus or minus for my velocity of my source must make my fraction bigger. Now that depends on where Vs is. Vs is at the bottom of this fraction. How do you make a fraction bigger when you change the bottom of it, when you change the denominator? What I've got to do is I've got to subtract away from the bottom. So I've got a minus Vs. This is what I mean to change my Doppler fraction to match my prediction. So that means that if I take away from the bottom of my fraction gets bigger. And that's what I want. I want my fraction to get bigger because I want the frequency of my listener, there it is, my frequency of my listener has got to be bigger than the frequency of my source. And that's where the Doppler fraction is coming in. I've got to subtract Vs to do that, to make the fraction bigger. And then eventually you can go into your step 3, and that's substitution. Now, just remember that whatever you're doing, your frequency listened must be larger. You might say, Phil, this is really, really difficult. This is very complicated. How do I know if I've done it right? Well, there's a very easy way to test. And in fact, step 2, you can mess up completely. And I don't want you to be afraid of making mistakes here. You can mess up step 2, exactly as I did. Okay, so you can mess up step 2 completely, and you can still fix it. That's a really great thing, because you'll be able to tell after your substitution whether or not it worked. So my frequency listened is equal to my Doppler fraction now, which is greatly simplified, multiplied by the frequency of my source. Once you put in your numbers, you check. There we go. We're going to check as our last step. So if we check and we find that it's wrong, all that we need to do is swap the plus for a minus. We know that we went wrong in step 2, and that's okay. We can go back and fix it relatively easy. So your check relies on step 1, a good prediction. Objects getting closer, frequency will increase. Objects getting further, frequency will decrease. I think it's time to give them a bit of a break. What do you think?
Just a tiny little bit, because I can see you guys are posting on the page and you're actually understanding what's going on, but I do think they need a little bit of an ad break.
Okay.
A lot of information in a little time, right? So, guys, please just quickly go walk around, stretch your legs, I don't know, do some of this and stretch your ankles, I don't know, whatever you want to do. And Phil and I will be back right after the ad break. So keep posting and we'll check you afterwards. Welcome back, Matrix. I hope you stretched your legs. I know I did, because I'm really ready to hear what Phil has to teach us, because I can see you guys are posting and we're going to get back to your questions at the end right now. We're quickly going to get back to the questions, but I just want to say, Macmillan, thank you so much for sponsoring our show. Otherwise, we would not have had such amazing information passing through my brain right now. But anyway, getting back to the show, Phil, please take it away.
Thanks so much. Okay, well, let's just get back into those steps. So we've put them out here. Just make sure that you're following these steps. It's a really nice, foolproof way of figuring out what's going on with the Doppler equation and how to actually work on it. Now, the most important steps actually are the first and the last. Prediction. Whether or not you can say that the frequency will increase or decrease, that's really important. If I know it's going to increase and I check at the end, and please, this check is not a waste of your time. It takes half a second inside your brain saying, wait, this doesn't match up with my prediction. If it doesn't match up, you chose the wrong sign. You didn't choose plus when you should have chosen plus, or you need to change it. You need to go back to step 2 and figure out what's going on. Okay, so just once again to summarize what I'm talking about in step 2, my Doppler fraction over here, the thing which I love and know, this thing is the thing which is going to be changing our frequency into the way that we want it to. That's the Doppler fraction. It's because of these velocities that the frequency is going to change. You need to choose a plus or a minus on the top or the bottom to try and figure out, is it going to change the frequency source to be a higher frequency or a lower frequency? So let's just make sure that you're going to change it to the right one. But even if you don't, Step 4 is there to help you out. Substitution and solving seems to be the thing which people love the most. People want their gratification. They want their final answer, because substitution and solving is what gets me marks. But I'm telling you now, if you don't do steps 1, 2, and 4, you're bound to fail matrix. Okay, you're not going to fail your end of your exam, but you're not going to get this question right most of the time. If you just jump straight into the equation and just go, I'm just going to put in some numbers, great, fantastic, and some numbers come out, and you go, wow, that's fantastic, I did the Doppler equation. The problem is you went in there blind, you came out blind, you didn't understand what was going on. So please, 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 matrix. The steps for success: prediction and checking. Definitely the way that you understand Doppler. If your prediction and checking don't match up, that means that I didn't do the right steps in between, and this is the way to do it. Okay, so now, as I said, we're going to jump into some exam-style questions. In fact, this one came from the March exam in 2011, and I really liked it because it was a very good example of how Doppler is tested inside a matric final. In fact, this is from a matric final. Now, if you look inside our online notes, guys, grab them. It's got this question, it's got some solutions, it's got great links as well to some explanations. It's got this question nicely worked out there for you, so please print it out, follow it, and download it. Okay, so let's start going through it. So now our question, and it always seems to be question 6 in some of these exams. I'm not sure if they're going to keep on this trend, but question 6 says to us that I've got a whistle of a train. So what we've got here is a source. So here's my whistle of my train. Okay, it emits sound waves, and it's quite important that we know that there are sound waves because we know how fast sound waves go. So it emits sound waves of frequency 2000 hertz. So here we've got this train which is traveling along, which is giving off sound waves at 2000 hertz. What we've been given is two things. We've been told which one is the source, and we've been told, more importantly, what is the frequency of my source. Now, there we go. So let's write that out. That is my frequency of the source. It's very vital that we start identifying information as we go. Okay, so let's read further. Let's highlight as we go, and I recommend you do the same. So it says a stationary, meaning that I've got zero velocity on my listener. So VL is 0, and that's really important as well, because that's going to help me with my equation. So the velocity of my listener is equal to 0 meters per second. Very nice, because that's going to make my Doppler simpler. Okay, measures the frequency of these emitted sound waves. Remember, you can't hear frequencies accurately unless you're a really well-trained musical professional. And this person is measuring the emitted sound waves as 2080 hertz, so 2080 hertz. The frequency changed. Doppler happened. So now we've got a new frequency. We've got the frequency of the listener. So what we need to do is we need to read a little bit further, and they actually go on to tell me the speed of sound in air, okay? The speed of sound in air is 340 meters per second. That is just that V inside that equation, and that's really useful as well. So let's start going through my questions. Let's see the systematic ones. Now, I want you to pay attention to the mark allocations here. It's quite important. So 6.1 is really, really easy, and the mark indication is 1. So it's going to be a really short answer, or a really quick answer at least. So it says, name the phenomenon. Really complicated word, but it's basically saying, what happened? What did we observe here? Responsible for the observed change in frequency. Well, that sounds very familiar. Observed change in frequency. There were some velocities involved. Oh, wait a minute. What we're doing is we're talking about the Doppler effect. Now, all we needed to say was that this was because of the Doppler effect. We need to know our definitions. Okay, so the Doppler effect, there we go. We've got our mark. We continue. Now it says, is the train moving away from or towards the stationary listener? Now here I've got to be very, very careful. I've got to now compare my frequency of my listener to my frequency of my source. Well, I see that the frequency of my listener is greater, so 2080 is greater than 2000. That means that the frequency increased. So here we go. That gives me my answer. That means that objects are headed towards each other. Okay, it's very vital that you understand that because the frequency which was listened is greater than the frequency of the source. I increased the frequency. It's headed towards my listener. Now, this is where the marks come in. It says, calculate the speed of the train. Now, I thought Doppler was all about frequency, but don't forget, there's parts of my Doppler equation which have got velocity. And in fact, we're looking for the velocity of the source. So let's write out our Doppler equation. Let's do my prediction. Let's change the Doppler fraction, and let's go and substitute and see what comes out here. Okay, so now my Doppler equation, just remember, is that frequency listened is equal to this really nice Doppler fraction, V plus or minus VL. And we're going to simplify this really greatly. V plus or minus Vs. And then my frequency of my source. Okay, so now the question is, how do I change that fraction on the middle part of the Doppler equation? How do I change this to be a little bit simpler? So what I'm going to do is I'm just going to switch colors for a second, and I'm going to explain to you how we can change all of this. Well, lucky for us, we were told that the velocity of the listener is 0. So that already simplifies things. We know that if we substitute in a 0 there, the plus or minus doesn't really matter. So the top is not a problem. But now the bottom is causing a lot of you a lot of angst. Do I choose plus? Do I choose minus? How do I know? Well, it all comes down to my prediction. 6.2 was a prediction. We know that the objects are headed towards each other. And that's quite important. Objects which are headed towards each other want a bigger frequency to come out. So I've now got to change this fraction to become a bigger number. How do you change a fraction to be bigger? By changing the denominator, meaning the bottom part of the fraction. What do I need to do to that bottom part of the fraction to make the whole fraction, to make this part bigger? Well, if you're trying to change the fraction, what I need to do is I need to take away from the bottom. I need to subtract the velocity of the source. If I do that, I make the fraction bigger. Now, we're going to test this out many, many times. So this is step 2 now. Step 2 is to change my Doppler fraction to be what we want. Then only can we go and substitute and solve. So we're going to do exactly that. We're going to do this really, really slowly. Just be absolutely sure that we've got something which makes a lot of sense in terms of this. I've got this fraction now. This fraction is going to be larger than 1. Why? Because I'm taking away from the bottom piece, the denominator. So let's substitute in my values. Let's try and solve for one of these velocities, and let's see what comes out. We can then substitute it back and see if it actually makes sense. Okay, so my frequency, which was heard or listened, was the person standing next to the track. What they heard was 2080 hertz. My velocity of sound in air was given to us as 340. So that goes on the top and the bottom in the place of V. Now, please, 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 learners, please be very careful. They have indicated that you might not be using sound as a wave. And in fact, you might be using sound in a different medium. So pay attention to which wave and how fast it's moving. Here we were told that sound is moving at 340 meters per second through air. So that's why my velocity is there. So now I don't have the velocity of my source, but that's not a problem because I've got everything else. I've got my velocity of my source, which is really nice. All right? So, okay. So what we're doing now is now we're going to simplify. We're going to try and find Vs. I think I've only got about 10 minutes, so let's try to get through this quite quickly. What we're going to do is we're now going to simplify this to find Vs on its own. Now, you matrix are saying, well, how do I dig something out of the bottom of a fraction? Well, let's start manipulating my equation. Let's start doing a little bit of grade 9 maths, and let's try and figure out what's going on. So, first of all, let's get things away from this fraction. Let's say 2080, divide both sides by 2000. So I've moved the 2000 across by dividing it. And now I'm left with this beautiful fraction over here, my Doppler fraction. Okay, and then I've got 340. Now this might look very complicated, but it's going to get a lot simpler in a moment. In fact, we can actually simplify things as we go. So if we take out our calculator, it's 2080, and I divide it by 2000. I should get a nice simple number there, and 1,04 is really nice and easy to work with, so let's actually write that down. So 1,04 is equal to this fraction on the right. Now, to get a denominator out, I need to get rid of the denominator altogether. So what am I going to do? I'm going to multiply everything by my denominator to get rid of it. So now I'm going to say 1,04 multiplied by my fraction of 340 minus Vs, and that's equal to 340. Now, matrix, you've got multiple ways that you can do this. You can FOIL it in and you can multiply everything in and then subtract and do your final division, or you can divide both sides by 1,04. And that's exactly what I'm actually going to do. I'm going to make sure that this is gone. I'm just going to get rid of it straight away. And that's actually going to help me. So what I've got now is I've got 340 minus my velocity of my source is equal to 340 divided by 1,04. Now there's only one problem with all of this. All I've got to be able to do is I've got to be able to get Vs on its own. So the 340 is in the way. My negative Vs will equal 340 divided by 1,04 minus 340. But now this is all looking a little bit mathsy for my taste, so what we're going to do is let's put this into our calculator and simplify it. So let's just go through this together. So I'm going to say 340 divided by 1,04, subtract from that answer 340, and what we get is a velocity, and that's negative 13. Really, really nice. So I get negative Vs is equal to negative 13, and if I multiply both sides by -1, or whatever your preferred method is, I get the velocity of my source is 13 meters per second. Now, we can go back and check this. What do I want to check? Well, now this is a little bit more difficult to check because I'm not actually checking frequency itself. But what I can check is the Doppler fraction. The Doppler fraction can tell me if I did the right thing with the pluses or minus. Okay, so the very last thing that we're going to do with this calculation is just quickly substitute into my Doppler equation. So I can say 340, which was on top. Now at the bottom, I can say 340 now minus 13, which is the velocity of my source. Now what I'm expecting is a number which is slightly larger than 1. And that's a sign that I did the right thing. If this comes out to be an answer greater than 1, and there it is, 1,0 something, that's a very good indication that I chose the correct plus or minus. I just want to go back and see what would happen if I changed that to a plus. What happened if I added Vs instead? What you will find is a fraction which is smaller than 1. And that's not what I want. That doesn't agree with my prediction. So what we've done is absolutely correct. I hope that you understand that we've chosen the correct plus or minus. I think we've got a few minutes to answer some questions.
Yes, everyone has questions for you, so let me just...
Fantastic.
Okay. Electronic Earl says, for instance, a stationary listener hears a sound wave from an approaching ambulance and then it passes him.
Aha.
What I'm not getting is which sign I'm going to use.
Ah, okay, very, very nice question. Okay, now he's talking about the Doppler fraction. So now we've got an ambulance which is either coming towards or away from you. So if we've got our ambulance and it's now going to go past a person, so it's either headed towards you or away from you. So now let's draw in the two positions and let's just compare them. So let's give our ambulance a little bit of direction, which will help. So my ambulance is headed off to the right on the screen. There's two places which you can stand. You can stand in front of the ambulance or you can stand behind the ambulance. Now you've got to do a little bit of prediction. Now this is my listener, and my listener is stationary. My source is moving. So what we're going to do is we're going to do a Doppler fraction for both. So for this one, where objects are headed closer to each other, I have to make my fraction bigger. The frequency must increase. So what I'm going to do now is I'm going to say V, and I've got to change that fraction so it becomes bigger. What should I do to the fraction to make it bigger? Well, I'm changing the bottom of the fraction. So that means I need to take away from the bottom to make my fraction bigger. Now let's see if the same sort of thinking applies to the other side. Now do I choose plus or do I use minus? Well, I know that these objects are headed away from each other, or they're getting further apart. So do I choose plus or minus? Well, I want this fraction now to get smaller than 1. I want it to decrease the frequency. How do you make a fraction smaller by changing the bottom? Well, you change the bottom to be a larger number by adding to it. And if I add to the bottom of a fraction, it makes the fraction smaller, and that's exactly what's happening when objects are headed away from each other. So when they're headed towards, I use minus Vs. When they're headed away from each other, I use plus Vs. I hope that answers Earl's question.
Yes. And then they said, and if it's stationary, both the, what sign should I choose if both the listener and source are at rest?
Okay, very good question. What happens when VL and VS are 0? What you will find is that the Doppler effect doesn't actually happen. Objects need to come closer to each other or further away from each other. It doesn't matter if you choose plus or minus 0, it's still 0.
Okay.
So source
That
and
answers the
listener will be
question.
the same frequency.
Yeah, perfect. That's what other question is there.
Okay, so while we're looking for some questions, I just wanted to bring up something which came up a little bit earlier in the show. And that was to do with redshift and blue shift. Now, I told you to think about the next time you go out and look at stars in the sky. Now, this applies to the sun, which is just our closest star. So now, star is giving out light, and it's giving out waves. Now, before they strike your eyes, what I want you to think about is what happens if the star is moving towards us, or as most of the stars in the night sky are actually doing, they're moving away from us. What's happening to the wavelength? Well, the Doppler effect actually occurs when you start taking a look at light waves as well. When I stretch out light waves, what I'm actually doing is I'm making the spacing larger, and what I'm actually doing is I'm changing the frequency of the light as well. I'm actually changing the color that the star appears to be. So what you will find is that when stars are moving away from us, I will find them to be slightly bluer, and I call that a blue shift. Now, this is one of the reasons that scientists very strongly believe that all the objects in the galaxy, all the galaxies in the universe are actually expanding away from each other, because most of those galaxies and the stars inside them are actually shifted to a slightly more blue color. Now, if the star is headed towards us, and I think this is the last thing I can actually do, what happens when a star is actually headed towards us? Well, what you will find is that those waves are slightly more closely packed to each other, and what you're going to find is that when you observe it, when you're looking up at the night sky, is that that particular star is going to appear slightly more red than it should be. And that is called the redshift. Now, very few stars in the night sky are actually redshifted. That means that most of the stars in the sky are actually headed away from us. The universe is still expanding, and this supplies a little bit of proof for the Big Bang. Well, I hope that sort of sums everything up. I think we've kind of run out of time.
Yeah. Everyone says that they actually understand it now, so I guess
Fantastic.
you did exactly what you needed to, and I understand it, and especially for me because grade 12 was only 5 months ago, but I know it's a little bit rusty, so it's okay. But grade 12s, thank you for tuning into our show today. Phil and I were so happy to help you out. Really, really, really thank you for posting and everything that you did. I'd like to thank Macmillan for sponsoring our show today. Very, very big thumbs up. And don't forget, you can download the notes, tutorials, and videos that we'll post at www.learnextra.co.za/live, or hit us up on our Facebook page at, hit us up on our Facebook page at facebook.com/live, or Twitter handle at learnextra. But that's love from me to you. Thank you.